Good day. Study Unit 2 is on random variables and probability distributions. So the fourth part on Chapter 8, which is on sections 8.7 up to 8.9, which is on page 210 in your textbook, please. If we look at the outcomes in a study guide, you should be able to understand the basic concepts of random variables, and you should be able to clearly distinguish between discrete and continuous random variables. In this part of Study Unit 2, we are specifically going to focus on discrete random variables, so you should be able to determine the probability distribution of a discrete random variable, and then we are also going to look at a special distribution of a discrete random variable, which is the binomial probability distribution. The random part in the name indicates that you do not know beforehand what your outcome of your experiment is going to be. For example, if you toss a coin, you know that your outcomes in your sample space is going to be heads and tails. But if you toss that coin, you do not know beforehand whether you're going to get a heads or a tail. So, if we look at the official definition, a random variable assigns a numerical value to each individual outcome of an experiment. And random variables are denoted by italic uppercase letters, for example, X or Y. Let's look at an example. Example 8.22 states that consider X to be the number of heads obtained in 3 tosses of a coin. List the numerical values of X and the corresponding individual outcomes. These will then be the 8 individual outcomes in our sample space. So if you count the number of heads, you can either have 3 heads, you can have 2 heads, you can have 1 head, or you can have no heads. So the numerical values that your random variable can take on can be 0, 1, 2, or 3. And these will be your corresponding outcomes from your sample space for each of those events. So this will be an example of a discrete random variable, and you will see from the following definitions why this was a discrete random variable. A discrete random variable is a random variable that can take on a finite number of possible values, like in our previous example where the number of heads could have been 0 up to 3, so we had 4 possible values. And another example of that is, for instance, let's say that a telemarketer contacts 5 customers, and we define our random variable as the number of customers that can place an order. Then the possible numerical value for that random variable can be 0 customers placing an order, 1 customer placing an order, up to 5 customers in total placing orders. Or it can be an infinite and countable series of possible values. So you do not know beforehand where that value is going to be stopped, but it will be countable and distinguishable from each other. For example, a police station that opens dockets on burglaries in a city. So our random variable is defined as the number of burglaries that occurs in a city. You know there will be 0, 1, 2, but you do not know at the end of the day how many there will be in total. For continuous random variables, we look at random variables that can take on any value in an interval or a collection of intervals. So here we are not working with integer values like in discrete random variables, but the values can be decimals. For example, the weight of babies at birth can, for example, be anything from 1.5 kilograms up to 4 kilograms, or the heights of adult males on campus can be anything from 1.6 meters up to 2.1 meters. The probability distribution of a discrete random variable is then indicated as a list of values that your random variable can take on, along with the probability for each of those numerical values of your random variable. That function in your probability distribution is called the probability mass function or the frequency function of your random variable x, and it's simply the probability that your random variable is equal to that numerical value. So the capital letter indicates the random variable and the lowercase x indicates the numerical value that that random variable takes on. Then the two properties for that probability mass function that also needs to be satisfied, the same as the properties for probability, is first of all that your probability mass function must always be between 0 and 1, including 0 and 1, and then the sum of all your probability mass functions must add up to 1 in your table. In example 8.23, they determined the probability distribution of the random variable x of the scenario in example 8.22. So these were our numerical values and these were the outcomes in each of those events. So since we had a total of 8 outcomes in our sample space, we can use that to calculate our probabilities. So where x had a value of 0, there was only one outcome in that event, so our probability will be 1 over 8. We had 3 outcomes where x was equal to 1, so our probability will be 3 divided by 8. And for x equal to 2, there were also 3 outcomes, so our probability will also be 3 over 8. And then where x was equal to 3, we only had one outcome there, so our probability will be equal to 1 over 8. And if you add all the probabilities, that will give you a probability of 8 over 8, which will be 1. So our two properties are satisfied. In example 8.24, they give you the following probability distribution. Then they ask you, calculate the probability that x is equal to or larger than 2. So we are going to look at the union of these 3 events, but since they are mutually exclusive, we can apply the additive law of mutual exclusive events. So we will simply add the probabilities for those 3 events. So the probability that x will be greater than or equal to 2 will be the probability that x will take on a numerical value of 2, which was 0.4. The probability that x will be equal to 3, which was 0.25, plus the probability that x will be equal to 4, which was 0.1. So if we add those values, the probability that x will be greater than or equal to 2 will be 0.75. You can try exercises 12a and 12b at the end of chapter 8 to practice these concepts, please. We can then also use the probability distribution of a discrete random variable to calculate the expected value of the random variable, which is denoted by E of x, or it's also called the population mean of your random variable, and it's indicated by me. In your formula, you will take the numerical value of x each time and you multiply that by the probability of x each time. You do that for all your numerical values for your random variable and you sum all the values. For example, from example 8.22, you will take the value of x times the probability plus the next value of x times the probability, etc. for all 4 values. So your expected value, your population mean, will then be 1.5. We can then also calculate the population variance and the standard deviation for our probability distribution. For the population variance indicated by sigma square or the variance of x, you take the numerical value of your random variable each time and you subtract your population mean or expected value. Then you square that difference and you multiply that value by the probability of that numerical value of your random variable each time. You do it for all your values of x and then you sum those values. Then to get the standard deviation indicated by sigma or the standard deviation of x, you will simply take the positive square root of your variance. So in example 8.27, they give you this probability distribution. So X could take on any of those 5 values, and they give you the respective probabilities. Then they ask you to calculate the population variance and the population standard deviation. The population mean was not given, so we will need that for the variance. So we can calculate that first of all. So similar to the previous example, you take your numerical value of X times the probability, and you do that for all 5 values. So if you add all those products, it will be 2, and then we can use that in our variance. So each time you will take the numerical value that X can take on, and you subtract the 2 from there, the population mean each time. Then we square that difference and we multiply by the respective probabilities each time, and we do that for all 5 values, and then our variance will be 1.2. And then for the standard deviation, you take the positive square root, so the square root of 1.2 will be 1.095. Please try exercise 12C to practice this. The next section looks at a special discrete probability distribution called the binomial probability distribution, and this is applicable to Bernoulli populations. So this means that each outcome or element in my population has 2 possibilities, either success or failure. But you shouldn't attach something positive to success and something negative to failure. If something is a success in a Bernoulli population, it simply means that the element or outcome that I select meets the condition that we are investigating. And then failure, then that item or outcome does not meet the condition that we are investigating. For example, let's say we have a batch of 20 tablets, and we want to determine the defective tablets in that batch. Then all the tablets that are defective will be our successes, and all those that are non-defective will be our failures, because we looked at all the tablets that are defective, so that was the success. And then if we observe one of those elements in a Bernoulli population, we call that a Bernoulli trial. And then these Bernoulli populations forms the building block of the binomial probability distribution. We can use the following properties of the binomial distribution to help us to identify when this probability distribution should be applied. So the first property states that the experiment consists of a sequence of n repeated independent Bernoulli trials. So it means that we only have 2 outcomes for each trial, success or failure. And since they are independent, it means that the probability of success does not change from one trial to the next. So it stays the same. And the probability of success is indicated by pi. And please note that this is a probability that will be given. It's just a symbol. It's not a mathematical value or 3.14. And then the probability of failure will be 1 minus pi, since that will be the complement rule, because we only have 2 outcomes in our sample space. And then what we want to determine for the binomial distribution is the number of successes obtained from n trials. The mass function that we use to calculate probabilities for binomial random variables is given by this formula. So for a binomial random variable, we want to determine the probability of k successes in n independent Bernoulli trials. If you look at this formula in pieces, this first combination, n combination k, there we look at the number of ways in which you can have k successes on a total number of trials, and you can calculate that combination on your calculator with that shortcut that we studied earlier in the chapter. Then we times the combination by the probability of success, and that will be to the power k, because we will have k successes in Bernoulli trials. And then for this part we have the probability of failure, and this will be to the power of the number of failures, which will be the total number of trials minus the number of successes. And please take note that the number of successes can be anything from 0 up to n. This is important. For instance, let's say I have 5 trials and I ask you what is the probability that you will have less than 2 successes. Then I need to do this formula for 0 and for 1. Then you should be careful of these phrases in tests or exams and the corresponding mathematical symbols. So the ones that are obvious is exactly, less than, or fewer than, or greater than, or more than. But the ones that you should be careful of is at least. So let's say I have 5 trials and I ask you what is the probability that at least 3 of your trials will be successes. Then you will look at 3, 4, and 5. But then let's say I ask you at most or not more than 2, then you will look at 0, 1, and 2. For example, in example 8.28 they state, suppose that the probability of successfully rehabilitating a convicted criminal in a penal institution is 0.4. Then they ask you to find the probability that 6 of the 10 prisoners are successfully rehabilitated. That means that our number of trials N is going to be 10. The probability of success pi is going to be 0.4. And the number of successes K will be 6. So the probability that our binomial random variable is equal to 6 will be 10 combination 6 times 0.4 to the power 6 times 0.6 to the power 4. So our probability will be 0.111. In question B, they ask you, find the probability that no more than 2 of the 10 are successfully rehabilitated. So our probability of success is still 0.4 and our number of trials is still 10. But now K can take on the values of 0, 1 or 2, since we want to determine the probability that X is less than or equal to 2. So that will be equal to the probability that X is equal to 0 plus the probability that X is equal to 1 plus the probability that your random variable is equal to 2. So you will apply that mass function 3 times for each of the values of your random variable. So if you calculate that, your probability will be 0.167. We can also calculate the population mean, the variance, and the standard deviation for a binomial probability distribution. So the population mean, or the expected value of X, will be given by the number of trials times the probability of success on each trial. Your variance will be given by the number of trials times the probability of success times the probability of failure. And your standard deviation will then be the positive square root of the variance. For example, we identified these parameters for example 8.28. So the population mean, or the expected value of your random variable, will be 10 times 0.4, which will be 4. Your variance will be 10 times 0.4 times 0.6, which will be 2.4. And then if we take the positive square root of the variance, our standard deviation for our random variable will be the square root of 2.4, which will then be 1.549. You can try exercise 24 on the binomial probability distribution. And I also want you to calculate the expected value of your random variable, the variance, and the standard deviation for the random variable, please.